thank you to the audience. My name is Horst Tratnik. I'm Managing Director at Fallensysteme. And Fallensysteme is a company who produces, develops and sells acoustic emission equipment. We talked the last day a little bit about acoustic emission, and David Thickett will talk this afternoon a lot about this. He has many great applications. And we at Fallensysteme, we have, let's say, 3 or 4 key businesses, and one is definitely research and development. And we're here in a group, in an audience of high-profile researchers, and that's why I really fit perfectly here, even if I don't get your level of expertise in your domains. What we are doing is we have all types of sensors, data acquisition systems, software, and for sure training, support, and that means also knowledge transfer, because we've seen many applications and we can help and guide you through the process to understand if acoustic emission fits to your problem or not. In general, we are worldwide represented in the United States, South America, so we have agents all over the world, and what we are doing is acoustic emission. And I know most of you know what is acoustic emission, but I just want to point out a few small, let's say, KPIs. One is we are measuring crack activity. Yeah? So that means if a crack is growing, that's something that acoustic emission sensing can detect. So that means it's a very small signal. The sensors can pick up displacement on surfaces of some picometers already. So if very small displacements, that's something that acoustic emission can pick up. We work in a frequency range from 20 kilohertz to 2 megahertz. That's the typical range for acoustic emission, where you can use this type of technology to detect acoustic emission waves propagating through materials. So that means you always need a load. And yesterday I've seen some examples for wood plates, for example, wood panels, where the load is temperature and humidity. And that's exactly what we have. You know, we have the load, in your case, for example, temperature and humidity. If then in wood, for example, a crack starts to grow, it generates waves in the material, and if you have one sensor, it can detect this signal, it can digitalize the signal. If you have more sensors, let's say 4 or 5 sensors, you can probably also localize it. So that's basically when we talk about acoustic emission, that's the principle in behind. And one important fact at the end, we can detect crack growth, but we can't size the crack. Yeah, that always means that we can't tell you about the size, we just can tell you about the activity of the crack. Yeah, the crack tip. For example, if that moves forward, that generates pressure waves. Yesterday we also talked about sustainability, our carbon footprint. Yeah? And I was in a discussion, part of a discussion where they said, well, on one hand side, we save energy, and we try to waste less energy for cooling it down and controlling the humidity. On the other hand side, you get bigger storages, you get more art that you have to put to the storage. The museums are growing, so it's always a trade-off. And yesterday we also had one slide where where someone has shown how the consumption of energy grows over the next years. And I think that's important for us to realize, because that's not only related to museums, to your business, to your industry. It's related to all the industries, because we all need more energy, and so we can save energy for sure. We all try our best, reduce by 20%, for example, but we also need carbon neutral energy sources. You know, and that's, let's say, also for us, kind of a business, because if you go for sustainable green energy in the future, which has a low or no carbon footprint, that means you have to maintain the complete chain from the production, from the storage, and from delivering this energy to the end consumer, to the industry, maybe to the Getty Institute. So we need also tools to make it safe and make it reliable. One example is Neom City. Yeah, because we have to produce this energy somewhere. I know here in California there are also many solar panels. There are many wind turbines. If you come here by airplane, you can see many parks. And one of the cities for Europe, where they build now a new hub for generating this energy is Neom City. That's, let's say, the fuel of Europe in the future, but it's in the Middle East, so they have to store this the energy, they have to transport it to Europe and distribute it in the channel. So that means we definitely need here for the whole chain solutions to make this also safe and reduce risk for a human. But where is acoustic emission in this area used? For example, at wind turbines for lifetime extension. Because now these days, some of the wind parks, they are already 20 years old. And the lifetime of these wind parks was designed for 20 years. Now we have two options. We tear it down and build a new one, which is not really the best solution for sustainability. So what acoustic emission can help is to increase the lifetime of these wind parks and to make it more sustainable for the future. There are, let's say, two main areas where acoustic emission can detect defects, or let's say can give an information about the condition of the wind turbine. That's on one hand, oops, wrong one. That's on one hand side, the turbine itself. You have moving parts there, and you can monitor the condition of the bearings and of the turbine in such a wind turbine. And on the other hand side, the tower, that's really something where they also have a lot of force on it, and they can detect if the tower is still in good conditions, can be used, or if you have to maybe replace them. Just some water. Another example where acoustic emission is used to extend the lifetime are hydrogen power plants. These hydrogen power plants, they struggle with, they call this cavitation. Cavitation, if you have a power plant, if you have a generator, cavitation are small bubbles in the water if this is turning, if the generator is turning, and this generates defects, or let's say degrades the turbine itself. And therefore they are using acoustic emission as well, because they can detect these type of cavitation, and they can get a grading. If there is cavitation, if there is a little bit cavitation or a lot of cavitation. And then based on that, they can use some parameters to adjust it, to bring the wear of the turbine down to a level to extend the lifetime as well. Okay, we generated now the energy. Now we have to store the energy for sure. There are several ways. If you, let's say, use hydrogen to store the energy, you have pressure vessels with up to 11,000 psi. That's really a lot. That's a bomb. But these bombs, they are on our streets, with these trailers. So to ensure that these are safe, let's say, trailers, they use acoustic emission to test these storage tanks after production, and at the next step for requalification after, let's say, 5 years. Another example is liquid hydrogen. They really go down to -405 Fahrenheit, which is really very cold, but it makes it liquid and not too much pressure. And that's something, if you need it like natural gas today, if you want to have this on site, here at Getty or wherever, you can use this, for example, to store this hydrogen. Or you can store this green energy in a chemical way, like with ammonia, and that's stored at -33 degrees Celsius at normal air pressure. That's a very common way, because ammonia is worldwide used for fertilizers, but now they also use it to have let's say, a more easier way to transport energy worldwide with ammonia. We all have our smartphones in our pockets. We have batteries inside, and the application for batteries here is to detect chemical processes inside batteries. Actually, I think most of you already have seen applications or defects of batteries when they burn, when the chemical process starts. And because acoustic emission is so sensitive, so you can detect the stress generated by internal defects, by chemical misfunctions very early. And this is something where the researchers for new, let's say, batteries are using acoustic emission to use this as one sensing technology to understand what is the status of the battery and when the chemical process, before the defect really is visible, starts. So that means that's one of the applications if you talk about batteries, for example. That's an example from the, let's say, from our standard business over the last 40 years. That means if you store gas, if you store oil, that's the typical applications where they use acoustic emission for requalification of these storage tanks or for pressure vessels. In any case, acoustic emission can give you always an information about cracks, leaks, for example, to not contaminate the environment. Leaks is also important for, I think, all of us, because nobody wants to lose water, energy, whatever is in pipelines and controlled over valves. So acoustic emission is used, like here at the ethanol plant. That's an example from an ethanol plant. It's also used to detect leaks. You know, there are service groups, they go out to these plants, they go to 20, 30 valves a day, check if they are leaking or not, give a report to the team, and finally the advantage or the benefit for the industry, for the owner, is they know which valves are leaking, they know how severe it is, and they can put this on their service plan to know, okay, what should be done in the next service interval, for example. In Europe, but also here in the US, we have a big topic with infrastructure, with old buildings. These are some examples from Germany, but also here from the US, where we have on one hand side post-tension concrete bridges. That means every bridge with concrete has tendons inside. They are pre-stressed, and after some years, if there is corrosion inside, they start to break. And if one or two of these wires are breaking, it's not an issue. But let's say if 20, 50, or if 30% of these wires are defect, then it's really a severe problem. So it can really break down, and you can't see it from the outside. Most of the time, they can't see it from the outside because the wires are 2-3 meters below the surface. So that's why acoustic emission is used for many of these bridges already, to prove the safety for people who are walking through the bridges, who drive through the bridges, and the same for sure also at tunnels, because nobody wants to drive through a tunnel and be part of the collapse of such a tunnel. So that's one of the applications in the infrastructure, also for buildings, for example. We also have pre-stressed concrete in buildings, and also there they already use acoustic emission to listen to the structure if tendon wire breaks are happen or not. And on the other hand side, steel bridges, it's more or less the same topic, just a little bit smaller scale, because sometimes you have cracks in these steel bridges. And a crack, that's what I learned, it's not an issue. But if the crack grows, that's an issue. What they do, what the engineers at the bridges are doing, they go out, they measure the length of the crack. Next week they come again, measure the length of the bridge, of the crack, and so on. And that's not really efficient. So what they can do, put a sensor to this crack, and the acoustic emission signal can give you an indication if the crack is stable or the crack grows. And just in case that it really grows, then they send an engineer there to verify how much it grows. We had a presentation about NASA. For sure, we are also customer or NASA. This is the Langley Research Center where I've been last year. We also have customers at SpaceX and NASA, especially for carbon fiber materials. Because what they are using, they're using the COPVs. Yeah? So this is carbon fiber material to store hydrogen and other material or other substances when they, in their rockets. And based on that, they are using acoustic emission to qualify the material, the carbon fiber, if it has delamination, if they already have fiber cracks. There are methods for acoustic emission who can give you an indication if the material is in good conditions or it already has defects. And that's what they are using. But for sure, not only NASA and SpaceX, all the other, let's say, industry partners who are using COPVs for various applications. That's now more closer to the conservation and cultural heritage. This picture here is V&A in London. Yeah, that's where I met Michael this February. I met Michael last year the first time, and he really gave me some headaches because it was really interesting for me to see that here in the cultural heritage industry, they have different problems than the standard industry. So we have to tweak a little bit the software, support him with changing the software to get the information he needs out of the software, out of the data. And finally, it's something that is really exciting because it's, from our perspective, in this niche market, acoustic emission, it's a market, it's an industry. And that's why I'm also here, because it's interesting to see which problems you have to solve and where you're working on. And in that case, it's detection of crack growth in furnitures, for example. But what you can see here is an example of having, let's say, termites or active bugs in the materials. So in wood, for example. This young lady here, it's Lisa. She's investigating on a figure in a church. If there are bugs inside which are active or not. And that's what she's doing with a portable system. They can go there, put the sensors for 15 minutes and see if there are if the bugs are active and if they're eating the wood, for example. Yeah, that's a common used method in Europe. Not sure if they do it here, but on the other hand side, it also works for termites, and that's another application in this area. Sometimes if you ship your assets from one country to the other, more from Italy, let's say in Europe, to Germany, it can happen that you have termites inside. And they have to verify if there are termites inside, and that's the quickest way, just to put the sensor on it, listen to the wood, and see if it's silent, let's say, so no activities inside, or if there is something going on. And then they have to do pest investigation. So finally, it's always checking if on one hand side pest investigation works, and on the other hand side, if there is activity inside. Material testing is another example. We have many customers who are doing rock sample testing. So if you have stone, or this is a salt stone here in this case, they do tests, they take a sample from the big brick, let's say, and if they do some tests on it, put sensors on it, they have the advantage that they can get localization of the damage zones in the software, also damages below the surface, because most of the time you just can see the surface, and that's what they are doing when they do characterization, for example, of stone. And one other example for us, it's about safety. We have a Ferris wheel, for example, in Munich, where they also have a system on board to monitor 24/7 if the Ferris wheel shows any kind of wear, over the time, and they can add this information to their service plan to go to specific locations where they get information from the Acoustic Commission to make service, to look deeper into it, if the wires are okay and so on, to have a safe and proven, let's say, environment here for enjoying going through the Ferris wheel. Okay, that's my last picture for today. Because today should be my segue now also to our panel discussion. We will talk about how to bring the industry and the other domains together with your industry, with conservation, with researchers. And what I learned is we have to meet each other like we do it now. Yeah, this event here, this summit is really fantastic. So many high-level presentations and insights about different applications in your field. But I think we have to extend it and to meet each other, also from other domains. And that's what I recommend. And that's why I'm looking forward to the panel discussion later on. What are your inputs? What do you think we can do to make meetings with people from all over the world possible, to exchange ideas, because every domain has a different perspective, and I think that values, this is a value that we have to share, and this is how we can grow together. Thank you.
Thank you very much for the very interesting presentation. Any question?
Thank you for your presentation, Sandy Lecomte from Institut National du Patrimoine. So you use these techniques to detect insect in the wood, but how you can distinguish cracks from insect, from cracks from hygrothermic variation in the wood?
Okay, it's a good question. Principle, crack, the pattern, the fingerprint, let's say, the Acoustic Commission fingerprint of a crack looks different to the fingerprint of active bugs in the wood, you know. And it's not only one crack, yeah, like when a crack grows, it's more like that you have eating intervals of these bugs inside, and that's what you have to capture. That's why you have to put the system, or let's say the sensor, a few minutes, half an hour to the unit, and then you see under let's say conditions which are stable, same temperature, same humidity. That there is something inside which eats the wood. So you can distinguish between cracks, because this is a singular event, in this short time, very unlikely, and hundreds of, let's say, bites, yeah, of wood when the bug is eating the wood. So you can easily decide what is what. It's more the question in this area, what type of bug is it? Yeah, that's research that they start in Germany at the moment. There are some guys very interested in to distinguish between different types, because they work, let's say they have also different fingerprints, let's say, of what they are doing, these bugs. But that's let's say the main difference between, let's say, the crack and the bug which is actively eating off the wood.
Thanks. We did it, and it was not so easy to distinguish cracks, because if we are doing the experiment during the winter, for example,
okay,
the insects are here, but they are sleeping. And so the house sensor need to be glued for a long time to be sure to have a right diagnosis on the object. It was not so easy. We use neural networks and so on. Okay. To distinguish the
interesting. We maybe later talk a little bit more in detail, but it sounds super interesting. Yeah, thank you.
I just want to comment, because that's an excellent question, and we were dealing with that in many cases before, because when you are monitoring objects, you may have those doubts. But you know, the thing which works very, very well is that looking at the correlation between the signal and the conditions, and in fact, if we have a strong correlation between the acoustic emission activity signals with the temperature, it's a very good indication of the insects. So one thing is like Horst described this understanding of the signal itself, but even if you don't have very much insight there, just looking at the correlation with temperature and humidity helps very much to indicate that. Thank you.
I saw that Antonio had a question.
Hi. We had to do a survey on the structure of a bronze sculpture. And we were looking for the location of the cracks. It's a Middle Ages sculpture, a lion, big like a real size lion. So I was wondering, at the end we used ultrasounds with the gel, and it was, we located some, but I was wondering if with your technique it could have been possible to do a complete map of the cracks.
If I understand you correct, it's bronze, so it's a metal kind of.
Yeah.
But we just can detect active cracks. That means not the crack itself. That's why you used ultrasound, and you have to put a force on this sculpture, on this figure. If you can do this, you can maybe, if the crack grows, I don't know if you want this, but if the crack grows, you can detect it. But it's not a technology that's working passive like ultrasound. It's really just listening and capturing active crack growth.
Okay. I was wondering maybe you could knock on the bronze and listen to the sound that comes out.
No.
Okay, thank you.
That doesn't. Sorry. Yeah.
Thank you. I was wondering, so you showed some example on wood and on stone, but textiles also are could be infested by insects. So do you have any example? Do you have any application on textiles? If textiles is good media in which this kind of acoustic waves could move, could be detected?
You have textiles, textiles having a very high attenuation. Yeah, it's like on carbon fiber, let's say, materials. Even if at carbon fiber, this COPVs, it's already hard because the speed of sound and everything is different in any direction. Yeah, so at textiles, I'm
almost speaking about natural fibers because these insects infest natural fibers, not carbon or glass fibers.
Can you talk a little bit louder, please?
I am speaking about natural fibers, only about natural fibers, because if you the carbon fiber or glass fibers could not be infested by insects, but also almost silk or wool are very often infested by insects. So do you have any example or any application on it?
No, sorry, I don't.
Okay.
Okay, thank you.
Thank you, Horst. I have two questions regarding to the application. So the first one is about any special settings needed to apply this technique, like a very quiet room, because from your picture, it looks like no limitations over there.
You don't need a quiet room. Yeah, it would work also in a crowded room because it's not audible sound, it's not airborne sound, it's structure-borne sound. So in many applications, especially in the industry, it's hard to talk to each other, but for acoustic emission, it's very silent because we start at 20 kilohertz, and depending on the material, we work in 100, 200, 600 kilohertz range. Yeah, so the audible noise is not a problem.
My second question is, we have the wooden furnitures to be monitoring the crack activities. So how long does the monitor takes in most cases we can, so for conservators, we're sure that, the crack is stable or not?
You know, this is something that Lukas yesterday mentioned. Sometimes it's very boring because nothing happens, because you don't know when the crack starts to grow. Yeah. In regular environments with no big changes or no change of the force, I don't know. Maybe Michael, you can tell a little bit, but that's really random. Yeah, that's my understanding. Maybe you can correct me, Michael. But if you go into a, let's say, temperature chamber and you can force the temperature and the humidity change, maybe it can go quicker. Yeah, until you get the first information. But I can't tell you. I can't say it's 2 hours and then you get the first crack growth. Yeah, it really depends on the material. But Michael.
So I understand it like that we just need to capture this pattern of the climate which you are interested in. So in typical application, we think like monitoring for a year is a good idea, because then we've got like a full cycle of the change of the climatic conditions. But if you think that something is representative or most severe in a particular season or something like, I mean, that depends. But it's important to know the pattern of the climate you're referring to.
Thank you so much.
Final question? Okay, no, thank you very much. Let's thank again all the speakers of this morning.